All right, good morning, everyone. Thanks for hanging in there. So yes, this is nearly the end. Before I continue and talk about the Jacobi-Trulli identity and the Cauchy identity for Schur functions, and then maybe at the very end, time permitting, I can say one or two words about Schur processes. Just something about the exercises that you handed in, was it yesterday or the day before yesterday? In any case, the ones that we looked at yesterday. Just a few quick remarks about that with the platistic notation, because it seems that in almost sort of all the exercises, I mean, it was done correctly, but not necessarily in the sort of most efficient way. So in particular, sort of two examples that came up. And one of them was, I guess it was really about determining what this was, okay, and maybe it was broken up into two steps, so let me just remove the B and just look at this. I think this was one of the parts of the exercise. And what most people did was, well, because all this platistic notation was defined in terms of the power sum, so turn this back into something about the power sums and then do your calculation and then go back. And so that takes a long time. And of course, that sort of defeats the purpose if every time you have to go back to the definition. So let's just do this very, very quickly. So remember, inside here, everything is alphabets. So the alphabet 1 over 1 minus q was nothing but 1 plus q squared and so on, just as if you're doing ordinary, right, arithmetic here. Well, okay, or so let me write this slightly more intelligently. Right, I can just all use the same types of symbols. So now I'm just summing up letters of my alphabet, right? We use this additive notation rather than set notation, so it was very convenient. But now we use the fact that this function is multiplicative. Okay, so in other words, it's the same and in fact I think we had a z here as well, right? So not that it matters, but let me at least repeat what was actually in your exercise. So I just keep track of this z here. Well, this is now a sigma on a single variable. So one letter alphabet. And, well, in general, if you have an alphabet and you compute this, it's just you get just a factor for each of the letters in my alphabet, and you multiply it by that z over there, and that's precisely your infinite product that you wanted to obtain. Okay, there's no power sums here. There's no. It's really because, well, let's not write it like that. It's really just one line, effectively. Okay, so that's how you should compute with that. Similarly, at some point, well, closely related to this, I think then you were left with the problem of figuring out, okay, because now if we take coefficients of that, we end up with the actual complete symmetric function. And the question was, well, what is this? And, well, most people realize that this is a polynomial in A of degree r. So it suffices to just figure out what this is when I replace, okay, so this is, we wanted to know what that was, but given that's a polynomial, I might as well try to figure out what this is, right, just for sufficiently many values, or well, maybe for any n, because if I know what that is for any n, then I have enough values to determine my polynomial. And again, people now started to do sort of somewhat lengthy calculations, but this is, of course, same thing. That's just an alphabet of n letters, where the letters are 1, q, q squared, up to this here. All right, and then I think in an earlier part you had a convolution formula for that, which says that this is, well, which says more generally HR of the sum of two alphabets, right? That's essentially a reflection of the multiplicative structure of the actual generating series. If you take coefficients of that, then it immediately tells you that you get, if you want to separate the two alphabets, something like that. Okay. So if I apply that over here, I get that I choose this to be my first alphabet, and then the second alphabet I just make that an H of one letter, which is just 1. So just going to give me a 1. All right. And now I use the fact that this is a homogeneous function, so I can pull out a q here. And now you get 1 plus q plus dot 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 q n minus 2. And essentially you have a recursion, because we wanted to figure out what this was. Right? This is the same as k from 0 up to r, q to the power k. And now we have just h of k 1 minus q n minus 1 over 1 minus q. And I apologize, some people can't read that, but in any case, we have a recursion, this object with n, and now we've just replaced n by n minus 1, and that was a recursion again you had in, we even referred to question number 2 or so, where you had shown that the Gaussian polynomials satisfied this recursion, and so you're done. Okay? So really, working with these things, use the multiplicative structure. Don't go back to the power sums all the time. That's only, we use that to define things, but right, it's much more efficient to actually learn to compute with these alphabets directly in whatever type of function you're using. Okay? All right. So let's now move on and talk about the Jacobi-Trudi identity and then the Cauchy identity for Schur functions. Okay, so, well, let's call it the theorem, because it's so the Jacobi-Trudi identity is a determinantal expression for the Schur function in terms of the complete symmetric function. Okay? So let lambda a partition such that okay? So if it has length less than or equal to k, then I can write the Schur function indexed by this partition as a k by k determinant. So of course, if you simply take it to be exactly the size of the length of the partition rather than adding some additional rows and columns which you could easily remove. So in any case, but it doesn't matter, it's still a valid result. And so now here we simply put the complete symmetric function on each of the parts of the partition, so plus j minus I. Okay. I also defined the skew Schur function. I'm only going to, although the proof is exactly the same, but you just carry a little bit more ballast, so I don't want to do that. If you want to have the theorem in the case of the skew Schur function, then all you need to do is, okay, so in case you're interested, but I'll just ignore these bits here. Okay, so certainly works for more general Schur function, not just the one indexed by partition, but in general by skew diagram. Okay? So clearly this formula makes sense. For example, if you just take a partition that has a single row, that is actually the complete symmetric function. So just note, okay, if we just have a Schur function, say like this, then of course it becomes a 1-by-1 determinant. And of course I'm not sure I remarked that earlier. So a Schur function on the single row is a complete symmetric function. The Schur function on the single column is going to be an elementary symmetric function. Okay? So, all right. So how do we prove this? Well, so there's a, there's a reasonably short algebraic way of proving it. And you can find that, for example, in MacDonald. But I like combinatorics, and that's not very insightful. That's just doing some lines of manipulation. So I'm going to, well, I'll give you a proof, although I'll be reasonably quick. So if you want more details, you can look it up. But hopefully all the main ideas, I can explain that. And so we essentially use a very special case of the Lindström-Gesell-Viennot lemma. Okay, so if you know what that is, great. If you don't know what that is, don't worry about it, because the case that we're going to use, I'll spell it out. Okay, so that's essentially tells you something about how to compute sets of, well, if you're interested in non-intersecting lattice path on some acyclic graph, and then there's some extra technical conditions. And we don't need any of that because we are just going to look at a grid, okay? Okay, so let's say, so the special case for us is for non-intersecting lattice path on a rectangular grid. Okay, and so as you can consider way more general graphs than that, but it would only take too much time. Okay, so all right, so essentially, so the idea that if I have a Young tableau, they're in one-to-one correspondence with, well, non-intersecting lattice paths, well, yeah, on a grid. That's sort of what I said. And I'm going to explain to you how this works. Okay, so let's say here, this is my tableau T. Okay, so I've only given you the shape here, but okay, so let's say I have a tableau on, so I'm not going to put in all the numbers on the letters 1 up to n, okay? So the usual thing, if I work with a Schur function in n variables, then I need to compute all of the tableau of the shape lambda of that Schur function, and you need to stick in the numbers 1 up to n, weakly decreasing along the rows, strictly, weakly, I should say, increasing along the rows, and strictly increasing along the columns. Okay? So let's also say that so the shape of my tableau, let that be, well, again, my partition lambda. And of course, what else have we got? We have this content of my tableau, and I'm going to, as usual, write that as some weak composition. And some people asked me yesterday, so yes, we of course have that the sum of the parts of my composition, right, because both are counting just the number of boxes in my tableau, so that must, if this is not equal to that, then of course there is no possible filling. Okay, so that's what we have on the one hand. So now I'm going to draw, and I'll do an actual example in a moment. So take a grid. So let's say that here I have row 1, row 2, up to row k. Okay, k was, so let's take that the length of my partition, I'm going to make that exactly k. Okay? There's no point there to take k larger than the length. You can just reduce it trivially. Okay? So let's just say I want to prove the statement for the length exactly k. So I've got k rows. And so what I do over here, I have a grid, and I go all the way up to n. That's this n here. And now over here, make this 0, this is the point 1, point 2, dot, 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 up to k. And now what I'm going to do is I'm going to construct lattice paths starting at these points. So let's mark the points. They're the starting points. Oops, yes, all the way up to k. So I've got, well, all the way up to k minus 1, I guess, because I started at 0. So I've got k lattice path. Each path will correspond to one row of my young tableau. And essentially what you do, so let's take a path I here. So this here, it's going to look something like this. And so it's going to end, well, in fact, I want this to be k minus I. So in other words, the last path is going to correspond to the first row, and the first path from the left is going to correspond to the last row. So let me also draw this in here. So it's some path, and I'll tell you how I construct it in a moment. And that's going to go up to lambda k. This is going to go up to lambda k plus I. So there's going to, oops, you can't see the difference between the, so that's the subscript plus I. And the last one is going to finish at lambda 1 plus k minus 1. Okay? Path like this, so you can make steps up and steps to the right. And so let's now just do one example. So if this is row I, and for example I have the numbers I plus 1, what I do, I start over here, and apparently, because I have two steps, two i's, I go up to height number I, and then I take 2 steps to the right. Now if I have, my next step up is at I plus 1, so let me get rid of this here. I take one step at I plus 1, and so on, till I precisely reach that. Okay, so let's write that up. Okay, so the ith path, or maybe I should say, because the counting of the path really depends on whether you count from left. So let's say the path starting at and again, did I do this? Yes, this should have been I minus 1, I guess, because we start at 0. So I get everything off by 1. So the path starting at I minus 1, okay, takes, well, so m k steps to the right, at height k if there are exactly mk k's in that row. If the corresponding row in the tableau has mk letters or boxes filled with, let's fill with the letter k. Okay, well, that wasn't particularly clear. Of course, much better to just explain this through an example. So here we go. All right, so this is my tableau. Okay, so for us, the length of, let's write down what the partition is. So the partition is 4, 2, and 1. Filling is, well, I've got 2 1s, I've got 2 2s, 2 3s, and a single 4. The length of my partition is 3, so that's going to be my k. That means I have 3 lattice paths. And so the last one starts at 0, and it only has a 3, so it moves up, it reaches height 3, it goes 1 step to the right, and then it keeps going up, and so it finishes exactly at, well, lambda 3, right, which happens to be 1. So now we take our second row from the bottom, start at 1, it has a 2 and a 3, so it goes up, I reach height 2, there's 1, 2, so I make 1 step to the right, I'm done, I go up again, I see another 3, 1 step to the right, and I'm done. I end up here, and that's position 3, which is lambda 2 plus 1. Okay, this is one shift. There's always this shift of the staircase partition that we're seeing all the time when we're doing Schur functions, right? That was to avoid in the determinant that we don't get 0. We need to have something that is strict. And here again, we want to avoid these paths actually touching. So non-intersecting really means they can't even touch. And, okay, so the next one, so that's the first row. So we start in position 2. I have 2 1s, so I go 2 1s to the right. I go 1 up because I reach height 2. I go 1 to the right. Now there's no 3, so I go 2 steps up. I've reached height 4, and there's a single 4, so I go 1 further to the right, and there I finish. That's position 6, and that's precisely lambda 3 plus 2. Okay, so hopefully that makes it clear what we're doing. Okay, so, well, so let's see what this means for us if we try to compute the actual Schur function. Okay, so the only difference, by the way, if I take a skew-Schur function instead of a Schur function, is that I need to modify my starting points. Now it's 0, 1, and 2. If I have a mu in there, it means that there's also a shift here at the bottom. But the whole argument is exactly the same, and I was already struggling to get my indices right and the shifts right, so I thought there's no point including that, but you'll have no difficulty just adding it in if you understand the argument, right? So, as I said, there's just nothing to be gained to do the more general case, but it's completely the same. All right, so S of lambda, okay, so again, we needed to sum, right, semi-standard Young tableau of, and we could have any content, of course, on n letters. So again, we always do this on n letters. So my x to the content of my tableau. And again, if this were a skew-Schur function, I never have mentioned that explicitly. It's just the same, but now it's just, the only difference would be that you do a tableau on the skew shape, okay? But, all right, again, I'll ignore that. Okay, so we write this. So, because the content, I want to choose this to be alpha, so it's some alpha here. Okay, I've got something like that. And now we're really summing over SSYT shape. So that's exactly what we have over there. I know what lambda is. I know what alpha is. Okay, and then essentially can write it like that. Okay, so there's a weight. So first of all, every tableau, I can replace that by one of these pictures. Okay? But of course, every tableau has this x to the power alpha, so I need to give a weight to each part, or each set of parts. But that should be pretty clear that the weight of a path is just a product. You take your xi, you just count how many steps it takes at height I. Okay, so in total I have 2 1s because there's 2 steps at height 1. Okay, there's 2 2s because there's 1, 2 steps at height 2. Okay, so I just, okay, so, well, essentially number of steps at, well, I'm running out of space again, at height I. And of course I can do this for each individual path. So I don't have to, this is the weight of the set of paths. It's of course simply the product of the weight of each of the individual paths, right? So this path has only 1 step at height 2, but if I multiply by the weight, so I can also talk about the weight of just a single path, okay, in the obvious way. So therefore, essentially, right, we're summing over, well, set of non-intersecting lattice paths, okay, where now each path, so that's just the, okay, where again, I have a starting point, so if I wanted to, I could indicate that my starting points, I'm not sure I want to introduce notation for this, but what did I say? That was going to lambda k, that was going to lambda k minus 1 plus 1, up to finally lambda 1 plus k minus 1, something like that. Okay? If you want to record exactly where your paths should start and where you should finish, and we should not intersect, and I should make this clear, not even touching. Okay, so with non-intersecting, they also mean that you can't have, all right, you can't have something like this. Again, The semi-standardness will just tell you that this won't happen. Okay, so not allowed. And now we just take, right? Well, in fact, I told you the weight of the path. I actually wrote it like, maybe it would have been better to, well, given that that's what I've done, let's leave it down here. Maybe it would have been nicer to have just the weight to be the exponent itself, but okay, doesn't matter. Okay, so how can we, why does this help? Just have another combinatorial set. Started with Tableau, now we have this set of paths. So what is the deal here? And that's sort of what these people realized. I can consider a more general set of paths. Let's just take all paths starting here, ending here, but I drop the fact that they should be non-intersecting. So I make my set much larger, okay? So here I've drawn two other paths for you that were not in my set of non-intersecting lattice paths, because here I have my first path, it's crossing this one here, and it's finishing over there, so that's clearly not okay. And here's another one. It's touching, which I also said was not allowed, okay? So I just make my set larger. And what I need to do, well, if I keep the same weight and I just sum over this bigger set, then of course things are going to be problematic. So now I also need to assign an actual sign to one of these pictures, okay? And somehow I want to assign the signs in such a way that all these additional pictures that I've introduced, they're just going to cancel out, okay? I want some sign reversing involution, so then I don't need to worry about that because they don't contribute, but they do make my sum a lot easier to actually compute. That's the idea, okay? So this is sort of what these people tell us to do. Add a lot more. So now we are just looking at, well, let me just, again, I'm making up my own terminology, sets of intersecting lattice path, okay? But we keep the same starting points. That I don't change, of course. But I no longer, right, here I really meant 0 goes to this one, 1 goes to that one. So these are the starting points. But I no longer draw an arrow here because I don't know who's connected to which starting point is connected to which end point. So all I'm recording is starting points and end points, and you can connect them any way you like, okay? Whereas here I really meant it in the way I had it over there. Okay, so end points is still the same, still that set, but in any order. And okay, the weight of a path as far as the axis is concerned, I don't change that. I still just look at how many, right here, this is height 2, 1, 2, 3 steps at height 2, so that would be an x2 cubed, and so on. But I need a sign, and what I'm going to do is essentially, well, I prefer to label it, and it doesn't really matter, so I prefer to label it, this is path number 1, because it's the first row of my diagram. This is path number 2. This is path number 3. And here the same. This is path number 1. It starts here. So this is path number 2. And this is path number 3 here. So you can see that 2 and 3 have actually swapped order here. Normally, path 1 finishes the most to the right. then path 2 is next, then path 3, and so on. But here, path 1 is still where it should finish, but path number 2 finishes at the leftmost position, and so on. And here, so this would be path 3, this is path 2, and this is path 1. So now I can record in a permutation essentially the order of arrival. So this path here, or this set of paths that was good, that represents my tableau, I simply say, well, path 1 finishes in the rightmost position, so I give it a 1. Path number 2 is next, that's the 2, and path number 3 is over here, okay? So all, of course, my tableau correspond to a set of non-intersecting lattice paths where the corresponding permutation is just the identity permutation, okay? So now if I stick in here the sign, let me call it the sign of a path. So all I'm doing is, that's just the sign of that corresponding permutation. For the tableau that I had before, I've just given them a sign 1. But any other path that is not a non-intersecting picture, like this or like that, well, it may still have the identity permutation. Here, the order is still right. The problem is that I have touching. Here, clearly the order is different, so it corresponds to a different permutation. One is still, the first path is still finishing the most to the right, so there's nothing happened here, but these two have swapped order. And now you can see what the sign reversing involution is going to be. Well, there's many ways you can choose it, but you can, for example, try to find the first problem. Okay, and what is first? Well, you can define your own first. Let's just say the first from the left. And, well, maybe in that column there's 2 intersections. If there was another path here and it crosses there, and then you can say, well, the first from the left, and then you go up. Okay, so you can determine your own order. Doesn't really matter. But in that sense of first, if I have found and this one, of course, there's only one problem, so this is always going to be the first, whatever order you choose. What you can do is just change. So here they are crossing, and I decide to change that first problem. If it's a crossing, I make it touching. If it's touching, I make it crossing. That's swapping, in this case, exactly where these 2 paths finish, so they will have opposite sign. So by pairing the paths like this, all of those additional non-intersecting, or these intersecting pictures will just pair up and cancel. Okay, so this is the sign reversing involution that we need. And essentially, none of these additional configurations here is going to contribute to the sum over there. Okay? Is that clear? I know again, in my notes I spelled it out in more detail, so it's hard to do this on the board, but hopefully you can see the idea. Okay? So these 2 permutations, obviously, they just correspond to, because there's one swap here, so this, of course, has sign 1, this has sign -1, and these 2 pictures just cancel each other out. Okay? So, therefore, this is the same. And now what I can do is I can just first fix my so essentially I have a sum here now over permutation, so let me make sure I write this down in the right order and don't mess it up again. So if we do this, so we have this sum over all paths now. Okay, so in particular, if I fix that order, that is, of course, giving me a permutation. And because we have k paths, of course, all of these permutations, right, they are in the symmetric group on k letters. Okay, that was again, the k coming from the length here, because I have k paths going on. Okay, and so that's going to be my sign, and I'm simply going to, okay, so I'm now going to fix the sign first, rather than taking a path and figuring out what the sign is. Right here, of course, I take the picture and then I determine the sign. Now I fix the sign, so that tells me in what order they should reach the top. Okay, and so now I can take the sum over exactly this set here. But now I know, like before, I can write an arrow. I know for every starting point where it's going to finish because I fixed my permutation. Okay? All right, and so if you do that correctly, again, I'm just going to write all paths, well, or all sets of paths. So again, I don't want to introduce notation for everything from. So as I said, now I can again determine, so in particular, the point k minus, and I think it's most conveniently expressed like this, I can say the point k minus I, or sigma I, okay, so if I look at all of the permutations, right, this is still the set 0 up to k minus 1, whichever way I choose my permutation, and I take the same finishing points as before. Okay, so this was, of course, going to lambda I, and then we had this shift going on, k minus I. Okay, something like that. And this is, I guess, for all I. Okay, so as I said, over here I just take all the pictures and then determine what the sign is. Now I fix the sign, so I sum here only over the subset, where I now exactly know again where each path is going to go. Okay, because the permutation is fixed. All right, so what is, and then of course I still have the weight of, well, that big configuration. So let me just say P, right? It's P1 up to P, well, P1 up to Pk. And this is the additional detailed information that I need. Okay, well, we're nearly there. Because now, for each of these paths, if I want to determine the weight, I may as well look, so again, let's imagine we're looking at this picture here, so we fixed our sigma to be 1, 3, and 2. I may as well consider the weight of each individual path and just multiply them together. Okay? So I'm really interested in finding all paths from a fixed starting point to a fixed ending point. So it's just something that's doing this. And the weights are determined every time when I go horizontal. If I go horizontal 10 steps at height I have x10 to the power I, and so on. So what is that? Just this, if I take all possible, so I fix this starting point, I fix this end point, and I can do anything I like, because I don't need to worry about whether I'm crossing or not. So these paths, they just behave as if they're completely independent, right? I no longer need to, here it's complicated, because this path I need to worry about what the previous one was doing, but that's no longer the case. So what is each individual contribution from a path going to be? I just want a generating function for a single path going from a starting point to an ending point. We've already looked at that heaps. What's that? It's very quiet now. Don't be shy. What is it? Sorry? Yeah, that's just the complete symmetric function, right? That's, of course, exactly where we're, unsurprising, because we're trying to prove the Jacobi-Trudi identity. So we better arrive at some point at the complete symmetric function. Well, we do. Okay, so, well, let's say note that if I now take a single path, all right, from a single path from I, okay, to, well, whatever. Let me say r plus I. Okay, so it takes r steps to the right. So how many x's am I picking up? In total, I need r steps to the right. So this is going to give me something that's homogeneous of degree r, right? Can't be any other way. Okay, so again, just the weight of that single path here. Okay, that's precisely going to be, okay, well, in how many variables? Well, we have n variables, right? So, for example, the contribution of this particular path here would be, well, only x2 cubed, nothing else, and so on. But you can, any path will correspond exactly to one monomial contributing to your complete symmetric function. Okay? So, therefore, we get exactly sigma sk sine of sigma. Okay, and now we get, well, what's complete symmetric function? We simply need to take the difference between the ending point and the starting point, because that's how many steps to the right I've taken in total. So that's over here. Well, so I need to take, of course, the product over all paths. I have k path, not just one, but as I said, they're all completely independent. And then the k path, well, if that's its endpoint, lambda I plus k minus I, take away k, so that just cancels, and I get a plus sigma I here. Well, just by the definition of what a determinant is, that's precisely h lambda I, okay, the sigma I that turns into a j, and minus I, and again, of course, that's on n letters. But once you've done this on n letters, it's still better to write the identity the way I have up there, because of course this is now an identity in the algebra of symmetric functions. It's alphabet independent, of course. Okay, so that's essentially it. Okay, any questions about that? So I know that's sort of rather quick to sort of go through the Lindstrom, Gessel, VNO, although we only do it on a rectangle where it's relatively simple what's going on. Okay? So that's the idea. All right, let's now, so why is this such an important result? Well, because this gives me an easy way to prove the Cauchy identity for Schur functions. And remember, if you have these Cauchy type identities, that will give you a statement about, well, in the case of the Schur function, and it was already in one of the exercises, it will tell us that the Schur functions are, in fact, right, form an orthonormal basis with respect to, and self-dual with respect to the whole scalar product. Okay, so can this go? Any more questions about this? Otherwise, all right. Of course, there's other ways of proving the Cauchy identity, and I already mentioned that if you, again, want to be very combinatorial like this here, you can try to use RSK, but that's reasonably involved, and I certainly have no time for that. So, okay, so theorem known as the Cauchy identity. Again, if you care about Schur processes, for example, you do care about Cauchy identities, so you can talk to Leo about that. Okay, so it says that if I take a Schur function on x, Schur function on y, then this gives you precisely the sigma of the product of the two alphabets. Okay? And our earlier result is that this was equivalent, so we immediately can conclude again, for the representation theorists here in the room, this will not come as a big surprise. Okay? All right. So how can we prove this? Well, we already know that the monomial and complete symmetric functions form a dual basis. So, in particular, I can replace, if I put a complete and monomial here, I know that this holds. And now what I can try to do is use my Jacobi-Trudi identity to maybe go from one to the other. Okay? All right, so let's try to do this. And so rather than starting, I mean, I can go both ways. I can start from this and substitute Jacobi-Trudi, or I can go the other way around. I find this slightly easier, but it really doesn't matter. Okay, we had something like this, and in fact, I'm going to assume that my alphabet X has exactly n letters, because after all, that makes it easier. And the same with the Y, okay? So for us, these are just normal alphabets here, x1 up to xn. Okay, so, well, the first thing, then, okay, so now I continue. Okay, rather than summing over partitions, I can just sum over, again, weak compositions. So alpha 1 up to alpha n. Okay, so this is again a weak composition. Okay, and then I get, well, let me first write, and I'm just going to write it like this. Sorry, that was a y. So y of alpha okay? So we've seen this many times before, right? That this h of lambda, that's just h of lambda 1 times h of lambda 2 and so on. So if I permute the parts of that partition, that product doesn't change. So as long as this alpha is in the same orbit as that lambda, this is just the same, okay? So again, you can first fix the Sn orbit of my alpha, call that lambda, and this immediately becomes h lambda. Now I need to sum this thing over all the orbits of lambda, and that precisely gives me the monomial symmetric function. So I think this manipulation we've seen many times before, okay? So now what I'm going to do is, because I want to get to something that looks like a determinant, so that's a little trick, I'm going to introduce I'm going to multiply and divide by the Vandermonde product. In Y. Okay? So let me give this another. Okay, so use, and I'm going to, okay. Okay, the Vandermonde product, that was what we had in the denominator of our Schur function. So that's just I'm not going to write it in determinant form. I find it easier to just work directly with the symmetric group. So that's just the same as the definition of the Schur function, but without any partition in there. Okay, so that's simply, well, I was going to do this on Y. Okay, so, okay, delta again was this staircase partition that we were seeing all the time. Okay, so if you don't remember, okay, so this is known as the Vandermonde determinant. Okay, so I can stick that in there, and so therefore is 1 divided by the Vandermonde, and I'll just write it more briefly as Y, and okay, I have a sum over alpha, I have a sum, I'll just write them in one thing here. H alpha of x, and then we have Y, and now I have Y of alpha plus W. I hope that it's something like this. Let me just check that I've got all my exponents right. Okay, well, I hope I do. Actually, I think first of all, I've dropped the sign. And I think I probably don't need this, right? I think it's probably, anyway, I think that's probably better. Okay, so now, sine here of W, hopefully you can read this. Okay, so what is next here? I'm just going to call this thing here something like beta. I think that's the choice I want to make. I'm just going to make a change. Yes. Okay, so I'm just going to call that beta. So let's see, I'm probably going to get myself into trouble, but let's see how we go. I get here, so rather than summing over alpha, I'm going to sum over beta now. Okay, so by making that change, of course, effectively what I had done is I'd first put this sum in this order so that I can actually change alpha depending on what my beta is, and then probably when I go back, I change the order again, but in any case. So now we are left here with H. This alpha here that is something like beta plus delta minus, that's going to look like that. That looks pretty much like the Jacobi-Trudi. And we have, of course, y just to the beta plus delta, something like that. So where do I put that? Okay, roughly like this. And this here, if I carry out the sum over the symmetric group, that's precisely my Jacobi-Trudi. Well, I'm cheating a little bit because I don't know if this is a partition, but the formula remains the same. And again, as usual, I'm running out of space. And so we still have this here. And what else have we got? We've got the Schur function. So now we got a sum over beta. I have a y to the beta plus delta, something like that. And I have a Schur function. S. And that's, I think, on the, keep track of everything, that's the alphabet, beta. Okay? All right. But now, remember that, so beta is still composition here, not a partition. But we had this remark, so recall that beta composition well, then there's two situations. If beta plus delta could be written as the permutation of a partition plus delta, then we had that S of beta was the sign of that permutation times the Schur function of the actual partition, and otherwise the Schur function was just vanishing, right? So if you cannot write your composition in such a way that it arises essentially by permuting a shifted partition and then unshifting again, then S beta is just 0. Okay, that was something we said earlier. So I can replace this. If I use that, I'm not sure how many stars we've got at the moment. Maybe 3. But our suffering is nearly over now. Just to be hoped that I get roughly the correct answer. So otherwise, it's all for nothing. Okay, so effectively, I get 1 over this. But lo and behold, I get precisely now the sum over partitions. Okay. And yes, so precisely together with that, because I pick up a sign, so, right, I have the sum over partitions now here. That's what I should have, something like that. Sum over the symmetric group, that was these permutations. Then I had the sign. Okay, so essentially I made that top change of variables, anything else was vanishing. So I can assume that it's only those cases that are related to a partition, as in that first line. And then I get y. Okay, so beta plus delta was equal to, and I already had, so this now, that beta can be replaced by lambda. And I think it's all going to be good, because this is precisely the sum over lambda. This here is the denominator, and this here is the numerator in the definition, the determinant definition of the Schur function. So indeed, we've transformed the Cauchy product using the complete and the monomial symmetric functions in terms of the Cauchy product of the, well, so this is therefore, because that's what I started with. So if I just take the very first line and I put that over here, then we see that exactly what we wanted. Okay, so that's the Cauchy identity. And I am running out of time, but let's do a few more things and then maybe at least finish up with some remarks on how this can be related to stochastic processes. Okay, so first, so we already saw that we have that the Schur functions are now, right, we have it here, form this really nice basis on the ring of symmetric functions. Let's very quickly prove this and then prove the Pierre formula, because that's the Pierre formula. Okay, well, I'll get to that later. I'll say what I need to say about it in a moment. Let's first claim this here, that if I take this scalar product with the skew Schur function, so it's just a generalization what we have over there. I mean, clearly if this mu is 0, I get an ordinary Schur function, then both left and right trivially give you this delta, Kronecker delta, okay? So this is just slightly more general, okay? So how do we see this? Well, so let the Littlewood-Richardson coefficients be defined as, if I take the product, that's essentially what I have on the right. Oops, let me start with Schur. If I take the product of two Schur functions, and I want to expand this again in the Schur basis, which of course I know that I can. And so these essentially are just the structure coefficients. Okay, again, in representation theory, this essentially tells you the tensor product decomposition, because these things are characters of GLN. So if you take the tensor products and you want to sort of know how this decomposes into irreducibles again, that's what these coefficients are. Okay, but for us, they're just some numbers, and there's really cool combinatorial descriptions of what these Littlewood-Richardson coefficients actually are. But, okay, well, they're certainly integers. As I said, they're tensor product multiplicities, but there's all kinds of cool combinatorics there, but we're not going to go there. All right. So therefore, so what am I going to compute? Okay, so yes. So I'm going to take the left hand, I'm going to take this as lambda over mu. That was my left-hand side. And I'm going to do this with an actual alphabet x, and I'm going to multiply this by mu of y and by S lambda of Z. Okay? And then I'm going to sum over lambda and over mu. Okay? I can always undo this if you don't like this, because I just take, right, these are different alphabets, so it's a basis, and so I can just extract the coefficient again, given that the Schur functions are bases. Okay? So what we can do now, well, first of all, you remember that's how we actually defined the Schur function. So if I sum over mu, that is just the Schur function on the sum of these two alphabets, right? And now I still have an S lambda here. But now you see I can use the Cauchy identity. I can use the Cauchy identity, so this is simply sigma 1 of x plus y times z. Now I use the multiplicative structure of the sigma. So that's x, z, sigma 1, y, z. Now I can again use the Cauchy identity. So Cauchy again, of course I use it twice. So I would get something like mu and nu. And that's going to give me a Schur of mu x, z, sorry, x. Of course, the Cauchy is separating these alphabets for me. That's the whole point. S nu of y, S nu of z. Okay. Well, here you can see if I take, well, let me, rather than extracting the coefficients, let me just do the same calculation on the other side. Well, no, yes. Now, effectively, I can already see here, let's just keep going rather than going from two ends. So I see I have two alphabet Z here. So according to my definition of the Littlewood-Richardson coefficients, I can write this as lambda, mu, and nu. Right, so what I'm going to do here, I take, right, this one and this one, they're on the same alphabet. So I can use that, okay? So this is here Littlewood-Richardson. So now I get S mu of x. I get S nu of y. And then I get, well, I stick that in here, C, and I had a mu nu, and that's now a lambda, and then I get S lambda of Z. Okay? And, well, you can see here that if I, okay, so let's interchange these, let's interchange mu and nu, okay? Because I see this doesn't matter, of course. This thing is obviously symmetric. So I make this the nu, and I make that the mu. And now look at this here. And look at that here. So if I extract coefficients, I'm done, okay? So let me write that down. Okay, so the final step is take the coefficient of, and of course I can't see what it is, S mu of y. What's the other one? Was lambda, I think. Okay, so take that coefficient, and then we're done. Okay. All right. So that's nice. So we have something slightly more. So let's just add that here to our list. So we have S lambda. Okay, I have a mu there, so let me just write the nu over here, and then keep the mu here. So now we know that that is S lambda, S mu, S mu. Okay. So apart from Cauchy, so we've had the branching rule, we've had Cauchy, and I need one other ingredient, and then I would have everything I need to really talk about Schur processes, and that is the Pierre rule. But of course, so fortunately I won't have time, but so that's Pierre rule. Hopefully I can say a few words. So if I take a complete symmetric function and I multiply this by, so this is just a special case of these Littlewood-Richardson coefficients, because I told you that the complete symmetric function, that's just a Schur function on a single row. So I told you, well, that has a really nice combinatorial description. This has one that's even simpler than the full situation, because all we're doing is summing over lambda such that, well, such that this skew shape, well, we had notation for it, such that lambda and mu are interlacing, but of course also I need to watch the degree, so this skew shape should have size exactly r, and then we simply get S of lambda here. Okay? So it's all partitions obtained from you by adding one of these horizontal strips. Okay? And you can already think of this in a way if I take the, so, which is of course the same, if I compute the generating function, it tells me, and let's put alphabets in, although it's not really important. Well, and the Z here. So now it's just all strips. I no longer need to worry about the size, but that size is captured by that generating function variable Z. Okay, so that's in generating function form. So for example, if you want to grow partitions, starting for example from the empty partition, you can think of this sigma Z effectively doing that for you. Well, in a particular way. Namely, you start with the empty partition, and you're adding in all possible ways horizontal strips. So every time you do this, you add one horizontal strip, but in all possible ways you can do this. You get a bigger set of partitions that now all consist of a single horizontal strip. You apply this again, you're growing a second layer of sort of a horizontal strip, but again you can do this in all possible ways that you like. And so you can imagine that you can grow partitions this way, essentially by all possible ways of how you can add horizontal strips. And there was this exercise, and I certainly won't have time to again on the board to talk about these vertex operators, where we related this to one of these vertex operators. And so effectively the vertex operator, you can sort of see this as an evolution operator because it acts similarly to this. So it's starting to grow your Schur function, and the process is that you're allowing addition of a horizontal strips. Again, if I'd had more time, so it's in my notes, which I'll scan, and Leo will put them up. So I have yet to prove this, but let's at least sort of complete the discussion a little bit. So there is a very well-known measure on partitions, well, not just on partitions, and this comes from a more general setting, this known as the Plancherel measure, where essentially, if you see what it does for partitions, you're adding one box at a time. Okay, so there's something like the Plancherel growth process, for example, which is essentially a random walk on Young's lattice. So the Young's lattice is what you get if you take partitions and you start growing them one box at a time. Okay? So before I prove this, let me at least, so I've said something. So okay, I'll draw my Young lattice the wrong way around because it's always a pain to start at the bottom of a board. So you would have an empty partition, for example. The only way I can grow, right? This would simply, you're figuring out how can I add one box. I get this. I get that. And so on. Okay. And, okay, so this will give you the growth process. Well, I haven't, so how do you go? So you need a transition probability, of course. So there's a really nice measure on, as I said, that's essentially the Plancherel measure on partitions. And so what is that? Well, you take, so this is my measure. That's essentially the Plancherel measure. You take all of the exists here where lambda is a partition of n. So this comes from the symmetric group. Is there a question? Yeah, oh, I've drawn that twice. Yes, you're absolutely right. That is a very unusual Young lattice. There we go. Thanks. Okay, so this comes from a much more general result in representation theory that essentially the squares of the dimensions of the irreducible representations, if you sum them all up, you get precisely your size of the group. So this is for finite groups, obviously, and okay, we say complex irreducible representations, and this is certainly true. So that allows you to define more generally a measure on finite groups. If I do this for the symmetric group, then these dimensions, so this is precisely, this is the number, so again that's the dimension of the irreducible representation of the symmetric group indexed by the partition lambda, but that we know that that's the number of standard tableau of shape lambda. So standard tableau is not like, we've been looking at semi-standard tableau. Standard tableau is you have n boxes and you have the numbers 1 up to n, and you can use every number only once. So now, of course, we are become strictly increasing along the rows and the columns by necessity because we can never repeat a number. Okay? So this will give you a measure, and you can sort of have a transition probability. So the conditional probability to go, say, to a partition lambda, well, let's say n that's sort of at the level n, so this is of, let's say that that is equal to a fixed partition lambda, assuming that well, maybe I should again use lambda here. Lambda n minus 1 is mu. Okay, so this would be level or the rank. Okay, so this is, of course, there's a rank in this lattice here. And, well, what is that? That's precisely f of lambda divided by f of mu and divided by n. This will give you transition probabilities to go down along your... So this gives you a random walk, a directed random walk on this graph here, which is not the uniform distribution on partitions, okay, because it depends on these dimensions here that play a role. Okay, so back before I prove the Pierre rule and stop. So here the process, which is that I don't have time to formally define, a Schur process is, again, a type of growth process, but rather than adding single boxes like we do in this Plancherel case, we're adding, for example, horizontal strips. Or you can mix it up, you can add horizontal strips and then remove them again. Now you get the situation of plane partitions. Or you can add horizontal strips and vertical strips. You can mix these things up. But essentially, it's in the same spirit as this, but it's, well, I'm not sure if you should call more general. It's sort of, but anyway, it's the same idea. And so you can see that this Pierre rule, essentially, because that's what it's doing, it takes a partition and it adds horizontal strips. Okay? So, and as I said, you can express it in terms of vertex operators, as was in the exercise, and you can use these vertex operators to essentially evolve your process. Okay, so unfortunately I have no more time to say anything about this, so let's just prove this Pierre rule, and then if you're interested, yeah, you can, as I said, look at my notes, or really much better start reading Leo's papers, who can explain this much better than I can. Okay, so, but in any case, next week in Sasimoto's lectures, although he's not going to do growth processes, but sort of these traffic models, but anyway, they are probabilistic models again, and they use these Schur functions. So there will be, you will see some actual applications of everything we've done over here. Okay, so let's finish up by actually proving this Pierre rule, or this growth rule for Schur functions. And I already take that left-hand side, and I'm going to do my usual thing. So, okay, so I start with the generating function form. Okay, so we have this. And the usual trick is to multiply this. So I think that's what I'm going to do. And sum over mu. I think that's what I had in mind over here. So I think that's what I am going to do. So let's see what happens. Okay, so then we get, so then the left-hand side gives me, after I do that, I have a sigma z of x. And now, well, you can see I've got two, so I can again apply the Cauchy identity. So S mu of x is mu of y. So this is sigma z of x. Do I want the z here actually? Do I care about it? Yeah, I can keep sigma z, it's all right. I actually, and I get over here again, I just get the product of the two alphabets. I got this. Now, sigma z of an alphabet x is the same as sigma 1 of that alphabet multiplied by z. Okay, so just treating z as a single letter alphabet, and then I take the Cartesian product of that single letter alphabet with x. So that's sigma 1 of zx, sigma 1 of xy. Well, again, I use the multiplicative structure. So this is zx plus xy. And now I do my usual thing that I can compute with these alphabets as if it's normal addition. So this is just y to which I've added one letter, y plus z. But that's again multiplicative. And hopefully you can remember that we already had a rule for adding a letter to an alphabet. That was the branching rule. Okay, so it was a different kind of growing. That's not growing your actual partition. That's growing the number of letters in your alphabet. Okay, so, oops, can't move this up. So branching rule tells me that this is sigma 1 of x times, well, what was the branching rule for adding a letter? That was, okay, in terms of the complete symmetric functions, it was something like, am I going to do this in actual, I think I'll spell this out in terms of the functions itself rather than at the level of the generating function. So let's first, in fact, I can do this slightly more conveniently just in terms of the Schur functions itself. So let's just write it as I said, I don't want to do it at the level of the generating functions. I'll just do it at the level of the Schur function here. So that's Schur function also here, y plus z. And so now I use the branching on the Schur. That's better. Okay, so this is lambda s lambda of x. Okay, and then we had, that's all mu, again, that are now smaller than lambda, and again they should form this interlacing, or in other words the difference should be the horizontal strip, and this gives me z to the, again, the difference between these two partitions, this Q shape, and s mu of y. Interchange the order of the sums and extract the coefficients of s. So again, you can see I've got this over here, and where did I start? I multiplied by this. So now if I extract the coefficient again, same thing as before, I'm done. So effectively, so what have I used? I've used the Cauchy identity, so really the orthonormality of the Schur function. And I've used the branching rule. So now, again, take coefficients of that. Okay, so on the left-hand side, I'd multiply it by that, but now I take the coefficient. So I get sigma z of x. And over there, because I took that coefficient, these sums are swapped. It's sum over lambda. Well, if mu was interlacing with mu but smaller, then I'll just turn that around, and you see I get exactly what I wanted to prove. And as, oops, I should have the, that's no good. What is going on here? I'm making a mess of it, right? Did I want to generate? Now I'm completely lost as usual. What have I done? I want to, okay, so I want to do a little bit more. I wanted to get to that there. Oh, I took the, so I must have lost a S mu of, no, I'm right. I just didn't write everything down here. That's what I lost here. I lost an S mu of x, is that right? Okay, now it makes more sense. Okay? S lambda. I thought, where's my mu? But I just forgot to copy it down. So, as I was saying, we've used the Cauchy identity and we used the branching rule. And you get this Pierre rule. So the branching is sort of the dual of the Pierre rule. And again, if you look at this exercise about the vertex operators, so you can see that one of these vertex operators, so again, they're related to these. If you read the work of, well, for example, Okunkov, his first papers. Have I confused you, Jennifer? Am I telling lies? Is it just wrong? That's also possible. That, all right, so we had these. Again, I have no more time to define these. But you'll see in even the very earliest papers of Okunkov where he introduces these Schur processes, right? He uses essentially something that's known as fermionic Fock space. In the exercise, we only saw half of it when we looked at these Heisenberg commutation relations. So these can be defined as generating functions, right? So right, and then we're looking at these kinds of sums where we stuck in these plus or minus n's, those kinds of things, where we saw that these satisfy the Heisenberg commutation relation. And so these operators essentially commute up to a factor that you generate 1 over 1 minus z times w. If you take 1 with z, a plus with z, and a minus with w, and you can see 1 over 1 minus z. So that's precisely the kind of things that you see in your definition of your sigma. So it's not that surprising that these vertex operators, again, are related to creating or destroying Schur functions like an evolution process, because you see that they precisely generate factors that correspond to the factors that make up this sigma here. Okay? And so, indeed, again, as I said, for example, in the case of plane partitions, you start with something that's empty. You start acting with this gamma 0, which is effectively the same as acting with this operator. You start adding horizontal strips. You grow till you get to the middle, so your biggest stack of cubes, and then you start shrinking it down again. Okay, so if you sweep this across, you can view this sort of as a process growth, and then you can actually shrink again. So that's one of the examples. If you look at his papers, there's beautiful pictures of this, okay, which I obviously can't reproduce on the board. But in any case, it's a pity that I don't have one more lecture where I could actually sort of tell you a little bit more about that, but hopefully you'll still get sort of a sense why these objects are useful if you want to study these growth processes that are related to partitions and generalizations thereof. And I think I'm already way over time, so thanks very much. I'm leaving Tuesday sort of noonish, so it's certainly Monday and the weekend. If you.
So